be a nested class for the matrix class?
Yeah, the proxy class.
Yeah, so I saw the name of the class, and I realized that both class and for are colored purple. Is it because it's actually an identifier on itself?
Let me, I think it's just the prettifier, the code prettifier. I'm writing a comment. Let me briefly explain the purpose, right? I intentionally didn't want to give detailed sort of, instructions, right? And let me sort of try to explain what is the purpose of something like this. So let me just use a piece of paper to kind of um, give you a brief explanation, and then if that doesn't help, then we can discuss.
All right,
Okay,
sure.
so the purpose is, first of all, that proxy class can be anything, any name that you want, okay? Because it's not something I care about. I meaning the client. So we have, let's say, define some object that is big, right? Or small, it doesn't matter really. So we know that we can't overload, we can overload the subscript, but we can't overload the subscript. The idea is that I can do this if I create, I'll just call it static SM. If I do this, then the compiler allows me to write code like this. But if I build this
Um,
myself,
Sorry, Professor. Are you meant to show something on the screen?
yeah, no, you
Yeah,
can see.
yeah, we
No, you
can't
can
actually
see.
see anything.
Uh, Actually, I kind of was okay. So static matrix that is defined somewhere on your stack, and you can write code like this. Now, with the template class, you do this. Right now, we can do this. And what we would like is the ability to do this. Now, we are not interested in whether this is efficient, right, or not. Certainly, you can write code that allows you to do this. You can write an overload operator that allows you to overload the function call operator, right? And write code like this. Now, you know, I think that this is more efficient than this, but some of your clients might wish this because that's how they deal with regular matrices. So we can provide this, but we would also like to provide this. So the question is how? So the idea here is this. If I overload the subscript operator, which we are familiar with, then the idea here is this. This particular operator is going to return a proxy class that is instantiated with some information about this object that is calling this overload. What sort of information would you need? Well, basically, I need to know who is the object. So I need a reference to this object because when you take a I'm skipping the template part, but the idea here is that if I have something like class proxy, let's say this is a type. It is not a data member. So this particular thing is the one that gets instantiated when you do this, but it contains data. What sort of data? Well, basically a reference to the object that is invoking this, plus this information, the row. And the idea is that from the client's perspective, it's gotten really dark here because of I think there's a thunderstorm blowing by. So this entire thing then evaluates to some object that got instantiated by this particular function, right? And what happens then is that this guy, so if I had written M subscript R subscript C, this entire thing will evaluate to this temporary object. It is being returned by a call to this. So that's why we call it a proxy class. And that particular class has an overload that takes the column and essentially references the matrix objects data store at the appropriate location. That's really all there is. Now, what you are required to do is provide two data members, a constructor, right? And that constructor is going to take this guy and an integer value, record them, and it's going to implement this particular function. And using the three pieces of information, it knows whose objects data store it needs to go to and how to retrieve a piece of information from that data store. Now, I might have an object. So did this make sense?
Yes, Professor.
So it gives you a facade, right? From the user's perspective, they don't know anything about any of this. These are implementation details. But internally, that's kind of what's going on. Now, one of the problems you're going to have is that if I have matrix const CM, again 100, 200, and I do this, let's say on the right-hand side, right? Let's say I have an integer variable. So in this particular scenario, this particular call is going to be implemented by the overloaded version of the subscript operator. All right. So you cannot use this class because this class can only keep references to non-const objects. So in my comments, I said, repeat everything that you just did, but you need a proxy, let's call it a const proxy, that is going to behave as a proxy to const objects. So you need two of them. And this will return, or instantiate, I should say, a const proxy. And that const proxy will get this value, keep that value in its data member, and it'll make a reference to this object that invoked it. And so there is some sort of a cyclic thing going on here. And that particular proxy, const proxy object then is going to have its const version of this particular overload operator instantiated or invoked. And then it'll use the three pieces of information, this pointer to a const object, this row and the C to go to that const object's data store and retrieve the information. So that is the difference. While these sorts of references, where did I do that? Yeah, this one, they're more direct. We don't need a proxy. The function call overload will directly access this object's data store because there's no indirection involved, and that's why this could be a bit slower, but convenient. That's all. So I hope this small explanation will give you guys the idea that, and then the second thing that you guys need to know is that if you take a type and nest it in the outer scope, right? This guy essentially becomes a friend to this class. So anything that matrix has is accessible to proxy. So we don't need to do anything special to get to the data store. So it's a behavior from the language for nested classes. And I think this should allow you to easily kind of name them whatever you want. There's no convention because the clients are ignorant of all of this. And it should be fairly simple and straightforward. Does that answer your question?
Yep.
Go ahead, ask.
Yeah.
Because it's far easier if everybody is listening in. Otherwise, individually on the chats, same question I have to type. Even though I asked everybody to just redirect the question to the main channel, right? Anybody else has any issues or questions?
The proxy classes, right?
Sorry?
For the hello, can you hear me?
Yeah. We couldn't hear the earlier part.
For the proxy classes, is it a must to have the class proxy within the class of the matrix itself?
It's the simplest. Otherwise, you're polluting the namespace, isn't it? The client, if you say something is called, let's say, proxy, then you're polluting the namespace even within the 2125 namespace, right? So nothing's to be gained. And who wants this particular class? Nobody. You've created it just for this particular aspect. So I think nested is the way to go.
Okay.
I mean, it'll work. It's just that if I accidentally use it, then your program won't compile. So nested is the way to go, in my opinion, in these things. Now, if there is a particular class that you wish to use for many other classes, there is a pattern. I think next week when we begin talking about templates, it's called the CRTP. It's an idiom, curiously recurring template pattern. So it's a little bit connected to this, but not the same. Wikipedia, for example, as a nice example. If you want every class that you build to have a counter, right? Maybe in your game you need counters for soldiers, queens, kings, whatever, right? And obviously, it's annoying to go and implement that in every single class that you build. And you have lots of other stuff, more important stuff to do. So that particular idea of integrating some sort of a base counter to every class that you build is what is called curiously recurring template pattern, right? And it uses the idea that private inheritance essentially is composition, right? We have actually seen this in many cases. And so anything that is using private inheritance can be easily done through composition. So we'll talk about that next class. Okay, there's a couple of things. So the main thing about, are there any questions about pointers? The smart pointers, that is? Because I'm going to put up some sort of maybe a lab. And also, just to let you guys know, I'm going to pre-add. I'm not going to wait until you guys get done with this assignment. I think your schedule is going to get tight. So I'm going to add assignments as I get them ready. Okay. And you might probably see one on Tuesday. If you're done with the other one, you can start. Otherwise, you can just kind of, get your other work done. And I won't sort of squeeze the deadlines. So everything is going to be just spread out, but it's really up to you how you want to proceed. Okay. So the unique pointer, I think, is the one that you will tend to most commonly use. And one of the things that we couldn't get to look at is if you are using polymorphic, if you're doing polymorphic behavior, right? Which is in your game, you may have a weapon and specialized versions of those base class weapon type, and you want to store in a container such as a vector pointers to these specialized types, but obviously the base type is the one that you have, and you want to do this in a manner where there are no leaks, especially given that things can die and come back and so on and so forth, right? And it doesn't really matter which container you use. All these containers will provide value semantics, and unique pointer provides exclusive ownership semantics, so there's no copy. So, but still, I think for unique or exclusive ownership, if that particular weapon, okay, let's say I don't know, I'm a pretty non-violent guy, so I don't know much about weapons, but let's say you have a rifle type, and you created an object, and you're putting it in a container, right, or a pointer. And that particular rifle is unique. Nobody else other than a particular thing is going to own it, and that particular owner happens to be this container. In that case, it's fairly straightforward to use the standard containers. And so I'll talk about that. And then after we are done with this, we'll briefly talk about shared pointers. We'll talk about cyclic references, weak pointers, and we will be then done with this whole idea of pointers, smart pointers. And hopefully, guys, I mean, if you don't have the time now, but soon for good management of your game, right, switch over to smart pointers. So let me sort of create something polymorphic. I believe I have something, but let me just go ahead and say poly something. All right, we'll start from scratch so that I can go ahead and show it to you from the bottom up. It's again fairly simple. So let's say we have a vector class, and then we need memory for the unique pointer, and then we'll print some stuff. So here's a really simple sort of, yeah, I'll call it pet class. Actually, I'll make it be a structure because I don't want the public-private part. So anyways, so this is the base class in your game. And Nintendo has made many games related to this pet business. So this is fairly, standard example. We first of all need a virtual destructor. So that's the first thing I do anytime I see something like this. And we'll make it be an abstract base class. Okay. So the idea here is that we cannot instantiate an object of type pet. Now, let's say cats and dogs are, the favorite pets that people tend to have. So we'll basically, and we want every pet to do something important, which is, I don't know, make some sound, I guess. And we'll make this be virtual too. And there won't be a default behavior provided by pet. So we'll let the derived classes do all the work. Okay, first of all, let's go implement sound. So what do cats say? Well, cats go meow, right? So we'll say meow. I'm not a cat person at all. I remember my son saying, "Hey, I want a dog," whatever. I said, "No way," because I'm already taking care of you. I don't want to take care of another thing. Let's go ahead and implement a destructor, and we'll just print. We'll get GNU to print the function signature in a pretty way. All right. So I just need to copy this once more, and then we have a decent enough hierarchy for testing. Anybody know what dogs do? Bow is too, kind of like angry. So we'll go arf. All right, guys. I'm not in the best of health today, so I might be kind of, I think it's some sort of weird flu. So I'll just go ahead and copy paste this. Okay, and now we have a hierarchy. Hang on, let's complete that. Okay, so now let's get into main. And actually what we'll do is we'll create a factory, right? I mean, we'll study the patterns later on, but this is as simple as it gets. So remember, our hierarchy consists of the base class pet, and then we have cats and dogs that are subtypes or specialized types. So our pet factory, right, is essentially gonna, maybe let's make it take an int. And if the int is odd, it's going to return cats, otherwise it returns dogs. I mean, this is where variadic templates come in handy, and we'll look at that next week because different, pets might require different different values to construct themselves. So that's where variadic templates come in handy. So what we'll do here is we'll simply check if x is even, no, odd, then return, we'll use the make unique because we're no longer interested in dealing with new and delete. So here I'm going to return a cat. So the important thing for us is the pet class. We know that a pointer to a pet can point to a cat or a dog object. So is this going to work then? This sort of like smart pointer, which encapsulates essentially, which gives you an interface for a pet pointer, can it be instantiated with a cat pointer? So that is essentially what we are interested in checking. Since they don't have any constructors, so I can just go ahead and do this, right? Otherwise, we return a dog. All right, so now I come in here, define, this is what you probably are doing. If you are using raw pointers, then this is pretty simple and straightforward. We change those raw pointers to be smart pointers. And the idea here is exclusive ownership. There's only one rifle or one cat and dog. Well, They're all going to be pointed to by these guys.
You spelled dog wrong at line 25.
Yeah. Thank you. So let's call it a vector of unique pointers to pets. Actually, we'll call it SPCA. SPCA, if you guys don't know, is the Society for the Prevention of Cruelty to Animals. Okay, and it's sort of like they take care of all the stray cats and dogs and so on. So that's what's going on here. So we are going to, let's say, place back the pointer, and so we call the factory function and we supply a value. And then we do this a couple more times. And so we have something we can test. So much of your game probably sort of looks like this, at least the low levels, right? You have a level information, and if your game is all about just pets, then there's no hard-coded stuff in main in terms of you're not dealing with a particular dog or a cat. Because anytime you talk about a cat or a dog in your code, somewhere in the game logic, then you're hard coding, right? It's sort of like writing a game or writing a piece of code where you sort of use the number 7 or 10 or whatever. And these are magic numbers. But if you do it like this and you encapsulate all of this code somewhere else, then what you have is a container that works. Now, what we would like to do is obviously for each one of these dogs, or pets, I should say, we want to make them do something, right? So I'll call it make sound for now. And hang on, did I make these be? So we'll make these be const. And these should be no except, but I'll let go of that for now. And yeah, P sound. This is how it works. Now, I'm not making any assumptions. Probably many of you already have this particular setup, but if some of you have a setup that looks like this, okay? So I would call this bad for now, right? Not that I'm critical or anything. I'm just saying it's bad because in my code, it's going to cause a memory leak, and I'll show you how that works. So basically, I'm going to go ahead and create or call my. I'm going to just go ahead and do this. I'm going to create a dog. I'm going to create a cat. And I'm going to create another dog. And anytime you're thinking for whatever, right? Part of the purpose of the midterm was for you to kind of stop. No, we don't want to do any more for loops. We instead want to do, let's say, something that allows you to kind of think functional, especially with C++ 20 around the corner. So what we will do is we'll write an algorithm. The for each is the standard algorithm. Think of it this way. You have a database, a container, and you want to go touch each one of the objects, right? Because you want them to do something. So what is it that you want them to do now that you got all your database in order? Well, in a particular point in your game, you want them all to make some noises. So that is exactly what you will do here. And you will reach for these for each algorithm, right? We have seen the count, the accumulate, but the for each, I think, is the most important algorithm. And what it does is that it takes the container, and next week we'll get into lambdas and all that stuff. But for now, basically we'll pass a pointer. And a pointer to the function. And this function essentially is going to call the sound algorithm. So this is kind of the state of affairs, let's say. I should have maybe started here before I ended up there. The base class is going to call the what's the term for it? The derived will call the base class. So we need to provide this. I'm not sure if this will work. Let me try. Let's just go ahead and do that. Yeah, I won't do anything because we'll just keep it empty. Yeah, that's what I was thinking. So what's this? Okay. So what that means is I have to go in here and do this. Okay. Oh my God, what's going on? All right, sorry guys. Okay. So we got our stuff working, but obviously there is a memory leak. You can see that definitely lost. And if this particular container is being passed around to all of the different sections of your code, okay, because there's the audio guy, there's the AI guy, there is the collision guy, there's so many guys who are dealing with this stuff. And somebody forgets because there is the AI guy who says this particular pet cruelly must die, right? And so, maybe the AI person is thinking, somebody else is going to take care of the, deletion part. So what you end up with, especially if there are constant additions, if this was a linked list and you constantly delete and add, well, obviously there are chances that some of these cats and dogs won't be properly released. The memory associated with them isn't going to be properly released. So what we really need to do is essentially call delete. Now, we don't know lambdas, but the simplest way, in my opinion, to do this would be to go ahead in person like this, and maybe just take your pet by reference and well, take it by value, it doesn't matter. Pet P and then delete P, and this should take care of it. But we may not remember to do this often, and so we have to physically. So we are using new, and you got to make sure that you'll have the physical delete. If you don't, then bad things are going to happen. So the counter example is this one, where we are using, I mean, we could have written a factory function for this one too, but so this is where things are, and I'm going to go ahead and not bad, sorry. SPCA are the good people. So what they do is they are going to make sure that they call the make sound, but make sound, the only way to get make sound to work is to use the get function. Do you guys recall? So that is going to be one way. This is a particular problem. Make good sound maybe is what I'll call it. And what we'll do here is we will pass it the unique pointer, to a pet, and we'll do that using a reference. Otherwise, we have to move it, right? So this is something that you need to remember, because these objects in this container, these pointers, are the only owners of these objects. So if you want to pass them, obviously by value without the reference, then you're transferring ownership. So here we come in and we simply say, okay, I want to make my noise. So when we get to lambdas, we'll know how to do this better. But right now, I'm going to go ahead and give our algorithm this particular thing, and we'll run the code, and then we'll run Valgrind, and you will see that there's no memory leaks. So I think this is probably the simplest way for you to kind of, if you're doing this, it's a very minor change. It can be easily implemented, right? And the only thing to remember is that everything must be done by reference, because this guy is the owner. And for example, if you have a dog object, and we know that one of the objects is a dog, so the middle one is a dog. So if I say D, I want to get the ownership from SPCA. I want to adapt, and the middle one is the dog, and I do something like this. So this is essentially of type unique pointer, right? And I want your dog. So I say, well, give me. And then this particular assignment is not going to work because the compiler is going to say it's not going to work. So you have to be able to kind of get the pointer and then move the contents. So we'll skip that part, and this is kind of what I wanted to show you guys. Any questions? There's also deleters and so on, but I think most people, when they tend to use unique pointers, they tend to use new and delete. We've already looked at new and delete in terms of placement new and delete, because we have our memory pool and we want to grab them from there. So if you want to use your own deleter, essentially that's sort of where you need to kind of go ahead and deal with. So I'm going to skip that part. Okay. All right. So the next step is to look at what is called shared pointer. And shared pointers come into play when you have something a little bit more complicated than this. So in your game, so let me shift to the, so that I can write. So the picture sort of looks like this, a little bit more constrained. So you have a low level routine, okay, that is instantiating objects, pets, cats, whatever you want, all right? So we'll just call them objects of type X, and we'll give them names. And this is fairly common in computer graphics, where sometimes the data is fairly expensive. This also occurs in databases, many scenarios where you have expensive stuff that has already been created, and you want many others to share, right? So the way we want to share is that we have a container. I'll call this container A, could be a vector, could be a linked list, what have you. And then we have another container, let's say container B. This is again also fairly common. So for example, the people who wish to render these things to the screen, they need a particular order, right? And there are many ways to do that. For example, back to front are based on, the particular portal scheme you're using, what have you. Then there are other people who are interested in AI, and they may have a certain way of classifying the database. So they may use graphs or whatever, trees, and so on and so forth. So what we have here is a pointer. This guy encapsulates pointers. So this guy is pointing to this. This is pointing here, and this is pointing there. And the idea here is not exclusive ownership like unique pointer. Instead, we want this guy to be able to also point in our game to this already constructed object, right? And these are expensive objects to constantly create. Maybe it takes a long time to load them up. So if you're talking about a console game, then there is a cost involved in streaming the data and so on and so forth. So as you can see, it's not exclusive, but taking care of the management of this entire thing is quite complicated. Why? Simply because if I don't need this anymore, okay? Because in my container, I'm done with using this particular object X1. Well, if I am not aware of others sharing, and we have a team meeting and we say, okay, please, no deletions. Well, this guy is going to follow that advice. This guy is going to follow that advice. So at a later point of time, this guy may also not need this object. So then we end up with what is called a orphan, right? Because it's just taking up memory, and nobody actually has a reference to that particular object. Or if you don't have the team meeting, as soon as I'm done with this, I'm going to go ahead and delete this. But then you end up with a dangling pointer, a pointer that apparently is pointing. And if you're lucky and nobody else comes along and uses this memory, it may work. It may work for a little bit of time. And then this guy says, you know what? I need to actually allocate a new object, X4. And possibly some of the X4's object memory is going to clash with this, and this suddenly is going to have problems, right? Intermittently. And then maybe the game hangs, who knows? So this whole idea of managing all of these different portions of your code, okay, and written by different people, and technically there are three people: one who did this, two who's managing this, three who's managing this. The code becomes really integrated and error prone. And so what we need is a mechanism where let's say if you're working on a game, and for others who are working on some other kinds of software, embedded or otherwise, we instead want to make the collision detection be better. We want the AI to work better rather than managing these low-level details. And that is what the shared pointer does. Okay. And it actually uses pretty integrated technology. And that's why 20 odd years, 30 years actually, if you go back to the 80s when C++ got invented. So this finally came into play in 2011. Java, JavaScript, C Sharp, all of them already use this technology, right? And they kind of obviously don't have stack-based objects. They create everything on the stack. But the problem that they have, okay, is that when you no longer need these people, these objects, we don't know when Java, JavaScript, all these other managed languages dispose of this particular, unwanted objects. C++, it's completely deterministic because as we just saw, rather than using shared pointers, if we use, if we don't use unique pointers, but instead if we use, let's say, shared pointers for each one of these objects, and these are the smart shared pointers, when this particular container goes out of scope, obviously it contains a destructor. That the particular destructor says, I need to call the destructor of each one of my elements, right? If it's a class-based type. And those destructors will in turn essentially destruct this, but in a managed way. So in a sense, when your level ends or when a particular function, the scope of a particular function is done, you know that these guys are going to be taken care of. But in the other languages, the disadvantage is that it's done automatically, but not under your control. So we say it's non-deterministic. So we use this some smart pointer called shared pointer without worrying about the entire garbage collection process. Okay, it's only related to this particular pointer. It's pointing to this object that is allocated on the free store. And if this particular pointer goes out of scope, then if there is some other pointer of a similar type, the shared pointer type, that is also pointing to this object, then this guy will go away without deleting this, and it's the job of this guy to take care of that, right? And it's really not the job of the shared pointer. Whenever you use a shared pointer to create an object of this type, we end up with the manager object. And this manager object will manage the actual managed object. I don't know what else to call it, so I'll call it managed object. And then you have your shared pointer. And you can have SP1, SP2, all of them. Basically making use of this particular object that is sitting on the free store through this manager object. And so these two guys go together. And if SP1, let's say, was defined like this, shared pointer, I'll call this X SP1, well, it's empty, right? So it's just sitting there by itself, taking up a certain amount of memory. Then when you say SP1, make shared an object of type X, and let's say we provide some values to initialize this object. This object is going to be given birth, obviously, on the free store. That's what this make shared function does. And then it creates this manager object. This manager object uses a technology called reference counting, right? Nothing to do with C++ references, reference counting. And that is what garbage collectors do in other languages. They use reference counting. And reference counting is actually a fairly standard thing. It's useful in concurrency. It's useful in distributed systems. It's essentially a way to keep track. And I think the example I gave you guys is this. We are all entering a room, right? A lecture room. And the idea is to minimize the waste of energy. So the first person who comes in turns on the system, lights, AC, whatever. And every person who comes in at the entrance has a bowl, and we put in a token. We go in and add our tokens. The first one says, oh, The bowl is empty, so I have to go do some stuff. And that stuff is this, right? Creating all of this, turning on the stuff. And then all of the others come in and they add their tokens. So there is a counter here. Initially it is 1, and when I write code that looks like this, SP2 is assigned maybe, right? Because there's shared ownership. So I can take the object that I'm referencing on the free store, and you can also participate in using this guy. So I can simply use the assignment operator to do that. And same goes for SP3. SP3 was given access to this using the assignment operator by SP2. So each time the counter increases because you're entering the room, right? So the counter is now 3. And let's say SP3 goes out of scope. Then it's like when you are leaving the room, you're going to go to this manager object and pick up a token. It doesn't have to be the same token that you threw in. It's just a token. And the purpose of the token is to reduce the counter from 3 to 2. Then let's say you go away, SP2 that is. Then it's like you're leaving the room and you're picking up a token from the bowl. Now there's only one person left. When that person leaves that particular room, well, the counter is going to become 0. Notice, it's not the job of the shared pointer to take care of deleting, okay? The shared pointer is going to have functionality that will reference this manager object and let it know that it is leaving, and the counter is going to become 0. Then it's the job of the manager object to go in and take this managed object and get rid of it, right? And so we don't need to worry about memory leaks because all of us were able to use it. Now this guy, this is not something that C++ can guarantee, right? This guy can go make changes, obviously, because there are 3 people sharing. So in this picture, this container can update this guy, this container can update this guy. Smart pointers don't deal with that particular problem. That is more of an application problem rather than a C++ problem. And so here the object is simply going to now be deleted, and this whole thing disappears. Okay, so that is essentially how shared pointers work, and as you can imagine, because of the infrastructure required to build this reference counting process, I'm going to sort of make an assignment to kind of get you guys to implement this because it could be useful. It actually could be useful in many different applications, right? I want to know, right? I'm a soldier in the army, and maybe I want to know how many other people there are alive, that is, right? So these are interesting questions that, you know, rather than using a global variable, we can kind of use something similar and rely on that. And maybe if you want this to be something that should be common, not for the purposes of shared pointer stuff, but everybody needs to know how many there are of somebody else, right? And stuff like that, then a reference counter would prove useful. Now, there are a couple of problems with this particular approach. One particular problem that you will have, and I'll use a linked list to explain this, is that you have a SP1, and the SP1 is essentially making a reference. So this is a linked list, right, to another node. So let me draw this properly. So we have the head that is of a shared pointer type that is pointing to this guy, first element in the node. So this is the data, and we have a shared pointer. And this guy is pointing to another guy. And this guy, let's say, is pointing to another guy, and let's create a ring. So rather than the last element pointing to null, let's make this essentially point here to this guy. So what are the counters set up to do? We have to draw the manager, but essentially I can simply write down the counter in terms of how many people are using this guy would be equivalent to this plus this 2. This guy is 1, this guy is 1, right? And if you want to delete the linked list, well, this guy cannot be deleted because there is this guy pointing to it. This guy cannot get deleted because it has a counter of 1. Somebody is pointing to it. And this guy cannot simply be deleted with this guy being deleted because it has this guy pointing to it. So we end up with a cycle. And even if you say get this particular smart pointer out of scope, it's not going to trigger the automatic deletion of the entire link of these pointers. So they introduce what is called a weak pointer. So if you want these sorts of cycles, then this guy should not have a strong, right? Because its lifetime and this guy's lifetime are not governed tightly, strongly that is. So we want a weak relationship. We want a strong relationship here, strong. But if you want to break a chain, then you need a weak link, and that's what a weak pointer does. So rather than having a shared pointer here, what you do is you make this guy use a weak pointer to point to the first element, if you so wish. And this weak pointer doesn't add to the reference counter associated with the object, right? So this guy is going to end up having a counter of 1. And once you begin the process of deleting, this goes away. And because this goes away, this will go away, and this can get deleted and so on. And there are other examples I can give you. For example, in some of your games, you obviously are building event-driven systems. You are waiting for some sort of a manager or input, right? The example that I can give you is something that kind of matches the observer pattern, for example. So you are a subscriber. In your game, you're a soldier, whatever, you're a subscriber, right? And so I'm just going to briefly explain. So you probably describe certain input events or any other event that you're interested in your software by using the generic type, let's say event. There could be many kinds of events, so that could form an hierarchy by itself. Now you are a party, an actor in the game who is interested, right, in getting information about events. So you have an IO manager who records events from the player and decides where these events need to be distributed. So let's just kind of look at maybe in general how that could be done, right? I'm just making stuff up. So the listener is probably going to have a function called I want to act on an event, right? If I receive one from somebody. And we'll talk about that somebody in a moment. So it might look like something like this, let's suppose. So this could be anybody in your game, any actor. They, go from here to there, right? Well, I'm going to wait until I receive those instructions. And when I get those instructions, I'm going to do that. So that is the listener. The person who might give you these tasks, sort of like the publisher, right? So you are the subscriber. This is the publisher. So this can be set up to follow the observer pattern, but today we are simply interested in trying to understand how we can end up if you indiscriminately use shared pointers. You think you're deleting memory, but you're not. So that is the only thing that I want to talk about today. So you have a registering service. Anybody who's interested, right? So what the observer pattern does is that it provides a interface for listeners, for publishers, so that you can have any kind of listener, register with any kind of publisher as long as they follow certain protocols. And that is the idea behind that. And I think some of you are interested in this. We'll talk about that later if you in the later parts of the semester. So what I have here, guys, is a registering service. So you can come in, listen, no, you can come in and say to me, hey, if you have these kinds of events that you deal with, well, call me, right? And actually what we are doing is we're implementing what is called the Hollywood principle. It encompasses pretty much everything that we do, right? Do you guys know the Hollywood principle? Has anybody explained that to you?
No.
Yeah, well, I call it the kids in the backseat principle, right? Like, you go on a drive, let's say, you guys don't have kids, but I do. And, when they were really young, it's always like, when are we going to get there, right? Every 2 minutes. And then if you have multiple kids, then you pretty much are getting these messages every 1 minute. So it's similar. You're looking for a role you're in Hollywood and you're looking for a role. So you call the producer, right? And you do all the whatever, the demo and all that stuff. And now you're anxious. So what you do is every day you call. Hey, did I get the role? Did I get the role? Did I get the role? And what the producer is going to say is that, look, stop being annoying. If there's anything, any news, I'm going to call you. Don't call me, I will call you, right? And so rather than the listener constantly polling the source every time to get some information, what we instead do is you tell me whenever you register with me, and whenever I have something interesting, I'm going to go ahead and let you know, right? So we call it the Hollywood principle. So I used to tell my kids, I'll let you guys know, right? And but that wouldn't kind of take care of the problem, as you can imagine. But this is the idea behind the whole subscription, and that is how modern, it's a fairly common thing in Twitter. I don't know, I don't have a Twitter account or Facebook, and I'm not any of these, but I can imagine, right? Lots of times when I subscribe to newspapers, TV channels, whatever, Netflix does that. They always ask you, hey, do you want to get notifications, right? Teams does that. So what you're doing is essentially you, the listener, are registering to receive certain notifications. And what the Netflix does is that it looks at the listener, right? All of us are clients, but it has already created lots of hierarchies. This guy likes Western movies, right? So every time I have anything to do with Western movies, I'm going to send a notification. So that is such a common principle now, right? And games, of course, use it because lots of AI, almost everybody wants to know about things. And the old way of doing things was centralized, where we have the main, and the main would say, okay, I'm going to throw this stuff in the global memory, and you know where to go look for, right? So at the top of each loop, everybody would go look at that particular memory location to see if the flag is on, off, whatever, and based on that, they would do something. But part of what we have now is sort of like better facilities to implement these sorts of things. So we were talking about the listener, we have the source, and we would like to register. So probably you want to send a reference, right? And you are going to send me a reference. Hang on. So we have listeners. Okay. You're going to send me a reference to maybe a listener, const ref. Okay. I hope all of this makes sense. Yeah. And then I register. Okay. So I know I am the source of these events and I know when to get you done. And the problem with this thing is that if you go ahead and do this in your game, then what happens here is this in the private section, let's say it's a struct. So I'm going to go ahead and do that. I need to keep a record of all the listeners who have registered with me. OK, so what I do is, since I cannot simply say I exclusively own you, that's not my job. I simply want to keep track of all the people who have registered. And let's suppose I use, I suppose that all of you are on the heap. So shared pointer. So I have a sort of like a vector, maybe or whatever, of listeners. But in my case, I have only one, which is you. So I'm going to essentially register you. OK, but there's a problem here. The problem is that we have the source and we have a listener. And remember, the source object and the listener object are themselves going to have, going to be created on, let's say, the free store. And so they have a shared pointer that is pointing to them, right? And there is a strong relationship. When this guy goes out of scope, this entire thing goes away. Similarly, there is a shared pointer here. This guy is going to have a strong relationship with this guy, obviously, because it created it. But now I've created a fairly strong relationship. And the problem is that when this guy says, hey, I'm ready to let you go, in other words, delete, the manager to this listener, as you can imagine, because of this particular call, is going to have a count of 2. One would be this, and the other would be this. And so this guy is never going to die, even if you think it is. It can only die when this guy goes out of scope. So we kind of created this mutual sort of circular, not circular maybe, but some sort of a mutual kind of lifetime association. Yeah, that's what I was looking for. And so not both of us have to die at the same time for the memory to be properly released. Otherwise, I think I go away, that this guy is gone, but we have this. So that is where the weak pointer comes in handy. And that's why they invented that. So this is going to have a weak relationship, right? In the sense that, I don't govern your lifetime. The source, that is. All I care about is sending you the event. And to do that, I lost some room here. But I might have a function such as, let's call it dispatch. And let's say whenever, I find out that there is an event, because that is my job, I'm going to go ahead and call the dispatch function. And I'm going to call the dispatch function, which essentially is going to have a list of listeners. In this case, there's just one, and basically do this, right? And so now you get the information. But with the weak pointer, what we need to do is the interface of this weak pointer allows me to actually get a strong pointer, a shared pointer to this guy temporarily, and then the counter is going to go from 2 back to 1 after I finish with my call. And the particular thing that the weak pointer does is that it allows you to, I think it's called lock. Yeah, listener dot lock. Here there should be an arrow, right? Because listener is a pointer. So when you say listener member, it means you are doing the weak pointer stuff. You're not dealing with the managed object. So this particular function lock essentially gives you the shared pointer. So it increases the counter to this guy. And if this guy is already gone, then this guy will return an empty shared pointer, which I should then check before I tell you. So that is how it works. And I've given you a link on the web page. I think in the entire web, Microsoft has the best explanations, examples, and so on, right? They don't have this exact example, but they have all kinds of additional examples if you're so interested. So that would be, in my opinion, the best place to get information, right? If you already have other sources, that's great, because the textbook is a little bit more concerned with how to use it, but not concerned about bigger examples like this one. Any questions, guys? Did I give you an idea of how shared pointers can be used?
Yeah, no questions.
Okay, so you got to be careful. Don't just go shared pointer everything, right? So in this particular example, where is it? So these should be shared pointers, right? If there are relationships between these guys themselves, then I think they should be weak pointers. Otherwise, you'll end up with, again, memory leaks. So let's check some code out maybe to kind of see how we can implement this. Let's see. Everything seems to be related to okay, well, we'll create our own poly shared. Actually, here, let's start with this, which is like the most basic thing, right? Just to give you an idea. So again, I'm using my string class, and I just created a very dummy, simple thing called name. And name uses our type to construct a name. So it's kind of very trivial. The main thing is to kind of understand what's going on. So we come here, and this is the syntax, right? I want to create a shared pointer. The idea here is that this particular object that is constructed on the free store, pointed to by one, can also be shared by others. And this guy is changing. So I constructed, and just like make unique, we have something called make shared, right? Because I don't want to use new at all. So make shared is a utility function that essentially does really nothing. It just basically calls new, and it uses two important pieces of technology, which we'll look at in the following week, which is forwarding and variadic arguments, right? Because I can call make shared in some other examples using only one parameter, but one argument, I should say, but here I'm using two. So for now, we'll just go ahead and use this and look at how to build it next time around. Okay, and then notice this is the syntax. Anytime you're dealing with the pointer itself, because the pointer is an object. One is an object. Within that object, there is a pointer to this object of type name, right? Through a manager object. So we think of this as the managed object name. But in front, between this guy and one, there is the manager object. I think I drew that here. Okay, that is the one that is going to keep track. So who is the one that is responsible for deleting? It is actually this guy itself in that sense, right? Because it is, how should I put it? The idea of getting rid of memory wasn't given to one or to two or anybody else. In the entire sort of technology that C++ created, they left it to the managed object itself to delete itself, right? And so one is simply adding a counter, a token into that bowl, which is the managed manager object. Sorry, I'm getting confused. Manager object manages the managed object. So in between here, there is the managed object. Okay, so I'm updating this so it works. And anytime you want the interface, okay, so you want the interface. So let's look at Microsoft. Actually, I looked at them. I was quite impressed because it is good. Doesn't want to show up. Okay. Yeah, so you should read this. So here, they talk about all of the interface, and I wanted to kind of go to the shed where they have some examples. And give me a moment. What is it that I came here to do? Okay. Do you see the? Yeah, this is what I came here to find. Okay. So the shared pointer class provides you an interface. All right. It's pretty big. There are a bunch of things in there. So these are all the sort of like the member functions. Get. We've seen that with unique pointers, so nothing much happens. Reset. Basically, we are giving up ownership and we are making ourselves be null. And then we have the use count, which tells, which makes a query to the manager object to find out how many other, references are being made to this particular object on the heap. So if you want to access any one of these member functions, you use the period. If you want to use the underlying object, the managed object itself, as we saw in the previous class, the class has overloaded the member to operator, right? Structure member of operator. And that is what we need to use. That's all I wanted to kind of talk about. So if you, for example, want to know how many objects there are when you use the period, the member operator. Okay, so here I'm directly accessing my managed object, sorry. And here I'm making a query to the manager object. Yes, I didn't screw that up. And then I do some stuff Notice I'm passing by value. It's not a big deal because this is going to compile and work. It won't compile and work with the unique pointer because you have to move. Otherwise, we'll end up with two people having ownership. Here, it's okay. What happens is that the reference counter associated with the object increases, right? And you can go to this particular function and update it. Now I'm making a copy of the pointer, but the pointer itself is pointing to that same guy that we allocated on the free store. There's nothing C++ can do about that. It's your problem. Am I making sense, guys? Because it is a crucial point, right? All of them are making references to the same object on the free store. The copies that are being made to the wrapping container class that is supposed to implement these RAII features. So this guy goes in and updates, right? And then you can print after you're done. And then I create a new shared pointer, which is null right now, but it's also going to share ownership. And then we can query the number and you'll see that the count has increased to 2 at this particular point because there are 2 people using this. And to give you the sense that both of them are referencing exactly the same object, we are making a call to the get function. What does the get function do? It returns the raw managed object. And since both of them are referencing the same, these two pointers should evaluate to be exactly similar. And that is I think it should compile. Oh. All right, so notice that at the end, what started off as ocean blue ends up becoming something else called seashells, right? And so there's only one object on the free store, but we have many pointers, sometimes 2, sometimes 1. And when the last one leaves, the manager object will ensure that there is no memory leaks. So this is really nice. All right, any questions? I don't mind getting some questions now because questions. As you can see, I've been talking, I talk a lot, so I'm going to give myself a little rest. All right, there's 155, okay? Somebody must have a question. I can't be that good. I try to be good, but I can't be that good. How many of you are confused with this whole pointer business? And I think we are done with the pointer. I think finally, there's a lot more, obviously, but I think I'm thinking, we should move on to new things. So what are the new things I'm going to be talking about next week? I would like to get rid of a few things because otherwise they'll kind of constantly be in the, where we are constantly sidestepping. So the first thing we need to look at is sort of look at anything new in templates, and the most important thing is variadic templates, nothing complicated. And once we get this done, I would also like to look at forwarding. So this is something that has been enabled by R-value references. So it's the other thing that got introduced in addition to move semantics. Then I wish to kind of take care of a few other things. I think we spoke of variant, but I would like to kind of reintroduce it to kind of show you something called optional. Optional is nice because many times, right? In fact, in the game that you're writing, if you were returning a pointer, you don't care, right? You just return. If it is now, well, you know, the receiver can check. But what if I'm supposed to return something else, right? That is not a pointer. How do I indicate that something bad happened? And so this guy allows us to do that. And by combining these things, we can kind of write some interesting stuff. So these are the three things. And once I get done, I want to give you some basic background about functional programming. So we'll kind of quickly look through some of the standard containers. For example, most of the common ones we have looked at. I haven't kind of maybe looked at the map, so I'll just kind of look at that. I will look at maybe the iterator pattern. We haven't built a iterator. So if I want to build a C++ style iterator, right? What does it take? And then jump into writing code that uses lambdas, function. It's a function called function, and allows you to treat functions like first-class citizens, like any other object, right? So we can compose functions from different functions, pass functions, receive functions. So it's a higher level sort of order of, and that is, I think, quite useful to know, because if you are working in a high data environment, like any one of these companies such as Grab or one of the online retail or whatever they call them. What do we call Lazada? What is it called? Online e-tailer. Yes, like Amazon, and places like Facebook, Twitter, for example, right? They generate so much of data, and all the data is really transformed similar to the way a GPU uses stream processing. So you don't have the ability to create a database and then sort of run algorithms on the database. Instead, there is a tweet that got sent, right? And that particular tweet will have some metadata. Who sent it? Who are the subscribers? Are a pointer to that in particular information. And these little pieces of metadata are continuously being transformed for Twitter to kind of come up with real-time information in terms of what is happening. They cannot store all that information somewhere and then process that data, because one, it's too slow, right? And everything that you know about what is going on your system is quite late. Instead, we want the ability to kind of implement a style of programming. Some people call it reactive. And that is sort of like essentially how modern data processing happens. And functional programming is a little different than the way we normally tend to program. Here, we're going to think of functions as first-class citizens. So it kind of adds to one of the things that you can do with C++. So then after that, I'm going to jump into more like static polymorphism versus runtime polymorphism. That should take us to the end, because a lot of the patterns do need us to understand differences between static polymorphism versus runtime polymorphism. So in many scenarios, we don't need to build a pet hierarchy that we built. We can actually use templates, right? So that is static, meaning we don't have the cost of a virtual function. So I would also like to take this opportunity to kind of give you some exposure to how actually virtual functions are implemented. If you want the ability to have virtual functions, but without the overhead in a particular environment that you're working in, which is closed, right? And not open to the entire world, then we need to know how to implement that particular idea. So that should take us to the final part of the semester. This is where I'm going to go. Now we should cover the standard patterns like template, adapter, iterator, factory, type erasure, and we'll give some of them in assignments. Some of them we'll just kind of look at it. All right, for today, I think if there are no questions.
Sorry, I do have a question.
Yeah, go ahead.
Sorry, so you mean to say that whatever we've been doing is basically static polymorphism?
Sorry?
So whatever that we've been doing is
no, what we have been
just...
doing is dynamic polymorphism.
Oh, okay.
Using virtual functions. So that I call that runtime. Static meaning we use templates, so it all gets figured out at compile time.
Okay.
And we'll look at some examples and some idioms that arise in C++ based on that. All right, if there are no questions, I'm done a little bit early, but last time normally I kind of seem to take more of your time, so today I'm really kind of done with what I wanted to talk about. All right, guys, if there are no questions, then I'll see you next week. So do not sort of panic if you see additional things showing up. It simply means the deadline is further away. It gives some of you an opportunity to maybe get things done quickly so that you can work on other things, whatever, right? I'll also today, tomorrow work on adding something for lab to see if we can kind of explore some of these pointer things and also explore some of the memory stuff that we did earlier. Okay. All right. If there are no questions, I'll see you guys. I'll see you next week.
Thank you.
All right. Thank you. I was just thinking maybe somebody might just chime in and say, hey, I have a question. So I'll just wait for a minute or two.
Prof, I have a question about Sun related.
Yep.
This is about the overseas internship.
Overseas?
Yeah, the Redmond one.
Oh yeah, the OIP. That's what.
Yeah, the OIP. Yeah. So, is there gonna be any news soon? What are the chances that we might be going?
I don't know, to be honest. I haven't heard anything.
Okay.
I can make some inquiries.
All right.
Right, and see if I can give you some sort of inside news, inside unofficial, that can never ever be attributed to Prasanna. Okay.
Thank you.
All right.
Okay.
All right. See you guys.
See you.
Bye.